said that those terms are zero. I don't understand why they're zero.
Okay, because what the dot product of x with y hat, x hat with y hat? Yes, zero. Because if you go back here,
Oh.
does that make sense?
Maybe.
So just,
Well, I'll ask you about it more after class.
okay. All right, okay. Now I pulled out all the gradient from the three terms, so you would have that, okay? Now, at this stage, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 terms. And each of these terms, for example, here you have unit vector x, and here unit vector y, unit vector z, right? So just if you think of this one as some constant, and this is a unit vector, so I can write this in a matrix form in the following way. So the divergence of E times the electric field plus E dotted with the gradient times the electric field. I can write it as the gradient dotted with a matrix, a 3 by 3 matrix, assuming that the first here is x hat, y hat, and z hat, representing the first column, second column, third column. Then I can write in the first row what from that? Ex times the unit vector x hat, right? And in the second column, first row, I can write Ex, Ey, y hat, or x hat. This should be x hat. And in the third row, I can write in the third column. So I can write Ex, Ez times the x hat. So you can do the same for the second and third row, and so x, so that's not good there. All right, so instead of the first term, if I consider this one, okay, x hat, y hat, first row, if we consider the terms that involve x hat, second row involves,
I think it's how you had it written over the matrix, so that whole column will be x hat.
yeah, so this one,
So I think the only thing you need to change are the x hat, yeah.
yeah, this has to be y hat, and this has to be z hat, and similarly, so this is what you would have. Ex, Ey, x hat, yes, y hat plus Ez, z hat, and Ex, Ez, x hat, Ey, Ez, y hat, Ez, z hat. So you can write a similar expression for the magnetic field term, which involves B here, and for this term, for this term, you can express it using a diagonal matrix, because b squared is bx squared plus by squared plus bd squared. So for the electric field, you would have that. Now, when you combine this along with the electric field that we obtain in here, and you can write these three terms in this form. So this one is the term comes from here. This is the term that comes from these two, and the gradient vector, you can use it. You can express it using one row matrix. So when you, after you get a similar expression for the magnetic field, you define the tensor quantity, which includes the electric field and the magnetic field, which is known as the Maxwell tensor. Then what's going to be the form of the force density? So what we have done so far is, so this is our force density, all right? This is our force density, and what we have done for the Maxwell tensor is for this part, okay? This part, you can express it as the divergence of the Maxwell tensor. So basically then the force density becomes the divergence of the Maxwell tensor plus minus 1 over c squared ds by dt. So that is going to be your force density. So now to find the force over the volume of the charge, then what do you do? Just give me a few minutes to finish this. What do you do? Yes, you integrate it over the volume, and you can find the force F. That's going to be the integral of F d tau. That is going to be the integral over the volume, the divergence of the Maxwell tensor d tau plus minus 1 over the speed of light squared, and the integral of ds by dt d tau. All right. So here, what can you do here? You have a divergence of not a vector, but it's a tensor. The divergence of a tensor over the volume. So I can write this as what? If you apply the divergence theorem, I can write this as a surface integral over a closed surface of the Maxwell stress tensor dotted dA. And this one here, if I take the time derivative outside, so I will have minus the d by dt 1 over c squared of the integral of the pointing vector theta. So that's what you get for the force for electromagnetic field. And this one, we will do an example. This one, if you are considering the static case where the electric field, like the previous example, where the electric field is constant and the magnetic field is constant, what would you expect for this static